Have you ever stopped to think about the fact that motion is, well, it's literally everywhere? From galaxies drifting through space to the atoms buzzing inside your own body, everything is constantly on the move. But how do we make any sense of it? How do we go from just watching things to actually predicting where they're going to be? That's exactly what we're going to figure out.
I mean, you see it all around you, right? The obvious stuff, like cars and planes, for sure. But it's also in the quiet moments. The air you're breathing right now. A single leaf fluttering down to the ground. All of this is motion. And believe it or not, physics gives us this incredible toolkit to understand it all.
So how do we get really precise with it? How can we know exactly where that car or that leaf is going to be 1 second from now or 10 seconds from now? That's the big puzzle we're going to solve today. And the answer, you might be surprised to hear, lies in a surprisingly simple toolkit. We're talking just 2 main tools. Once you get a handle on them, you can describe almost any kind of motion in a straight line. So, let's open up that toolbox and see what's inside.
Okay, tool number 1 is velocity. Now, we all use the word speed every day, right? But in physics, velocity is kind of like speed's smarter, more specific cousin. It's not just about how fast you're going, it's also about which way you're headed. And that little extra detail, the direction, is absolutely crucial.
And, there are actually a couple of ways we can talk about velocity. First, you've got average velocity. This is the big picture. It's like when you finish a long road trip and say, we averaged about 60 miles an hour. But if you want to predict where you'll be in the next second, that big picture view doesn't really help, does it? You need to know what's happening right this instant.
And that's where our friend instantaneous velocity comes in. It's exactly what it sounds like, an object's speed and direction at one specific, single moment in time. The formula you're seeing, don't let it scare you. It's just a fancy way of saying we're hitting the pause button and looking at a super tiny change in position over a super tiny slice of time. Kind of like freezing a single frame of a movie. You want the perfect analogy? It's your car's speedometer. Seriously, what that needle is pointing to right now, that's your instantaneous speed. Combine that with the direction you're heading and bam, that's your instantaneous velocity. It really is that simple.
All right, we've got velocity down. Let's grab the second tool out of our kit, acceleration. This one's a game changer. If velocity is telling us what's happening, acceleration tells us how it's changing. It's basically the engine of change for motion.
So, what is it? Well, at its core, acceleration is just the rate at which velocity changes. But here's the kicker, and this is super important. That change can be in speed, direction, or both. Stepping on the gas, that's acceleration. Slamming on the brakes, also acceleration. And here's the one that trips everyone up. Taking a turn, even if your speedometer doesn't move an inch, that's acceleration too. Why? Because your direction is changing. Okay, let's tackle a super common misconception. When you hear negative acceleration, your brain probably jumps to slowing down, right? Well, not so fast. It's all about how the signs of velocity and acceleration play together. The rule is simple. If they have the same sign, you speed up. If they have opposite signs, you slow down. Think about throwing a ball straight up. Its velocity is positive, it's going up, but gravity is pulling it down, so its acceleration is negative. The signs are opposite, and what happens? The ball slows down.
So, there you have it. Our 2 tools, velocity, which tells us how things are moving right now, and acceleration, which tells us how that motion's changing. Now, what happens when we put these 2 powerful tools together? Well, you get something incredible. You get the master blueprint for motion.
Now, for any situation where the acceleration is constant, and that happens a lot, think of a dropped object or a car braking smoothly, these 2 concepts give us just three master equations. They're called the kinematic equations, and honestly, they're like a crystal ball. They let us predict the future.
First up, we have this one. It's all about finding out your final velocity. All it's saying is that your final speed, that's v, is just whatever you started with, we call that v0 or v0, plus the change that acceleration adds over a certain amount of time. Super logical, right? A great place to start.
Okay, equation number 2 is the position finder. This is the one that tells you exactly where something is going to be. It takes your starting speed and then factors in the effect of acceleration over time. This is literally the kind of calculation your phone's GPS is doing to guess your arrival time. Pretty cool, huh?
And finally, our third equation. This one's like a special tool for a specific job. Its superpower, it connects your speed and distance without needing to know how much time has passed. Sometimes you don't have a stopwatch, and that's when this equation becomes your absolute best friend.
All right, enough with the theory. We've got our tools, we've got our blueprint. Now let's put them to work and see what they can actually do in the real world. This is where the magic happens.
And we're going to start with something you can literally try the second this is over, measuring your own reaction time. You know that tiny little gap between when you see something happen and when your body actually reacts? Yep, we can measure that. All you need is a ruler and one of our new physics equations.
So here's the setup. You get a friend to hold a ruler right above your hand. They drop it without telling you, and you snatch it out of the air as fast as you can. Now, the only thing you need to measure is how far the ruler fell before you caught it. And you might be wondering, how does distance tell us time? Well, because the ruler is in free fall, its acceleration is constant. It's just gravity. And since we know the acceleration and the distance, our equations can work backwards to find the time. It's like a little physics detective story.
So in the example we're looking at, the ruler dropped about 21 centimeters. We just pop that number into our handy-dandy position equation, do a little algebra, and boom, the reaction time was about 0.2 seconds. Think about that for a second. With a ruler and some high school math, you just measured the speed of the signals firing in your own brain and nervous system. That is just awesome.
Okay, that was fun, but let's take these same principles and apply them to something with, well, much higher stakes. Figuring out a car's stopping distance. This isn't just a fun experiment. This is the fundamental science that determines speed limits and saves lives every single day.
And this is where we get one of the most critical takeaways in all of driving physics. And I really want you to listen to this, because it's not what you'd expect. If you double your speed, you don't double your stopping distance. You quadruple it.
So why is that? It goes back to that third equation we looked at. When you solve it for distance, you find that the stopping distance is tied to the square of your speed. That little squared term is a monster. It means going 3 times as fast requires 9 times the distance to stop. It's a really powerful and kind of scary reminder of how these equations aren't just abstract, they have very real consequences.
So let's just recap. We started with 2 simple ideas, velocity and acceleration. From those, we got 3 powerful equations. And with that tiny toolkit, we can now describe and predict pretty much any motion that happens in a straight line. It's an amazing amount of power from such simple building blocks.
So, we've pretty much mastered motion in a straight line. But let's be real, the world is full of curves, right? So what happens when things aren't moving in a straight line? What about a basketball flying through the air, or a planet swinging around the sun? How do our tools handle that? Well, that's a story for another time.